Welcome back to this channel. My name is Dr. Arzu Jabra. I have a PhD in organic chemistry. I am a organic chemistry tutor and also a mindset academic coach for college students. I help students go from burnout and overwhelm to feeling a lot more focused, a lot more directed, and take better control of their time and their energy. It really helps them go from a low state of mind to a really high excited state of mind and actually help improve their grades and their focus in school. So whether you're going through MCAT stress or you're going through college blues, it really helps students become the best version of themselves. So in this video series today, we are going to go over aldehydes and ketones, and we are solving the Kaplan problems, and we are going over the Orgo chapters, and I'm going to be solving every problem at the end of the chapter and going through every problem one at a time, explaining the solution of these problems. And of course, if you have questions, feel free to link it in the description below. And also, or like mention it in the comment. All the links will be mentioned in the description. And also, if you want the PDF of this document, feel free to, again, in the description, feel free to use the Google Drive link where all of these PDFs are attached, so you can download those and practice these problems for yourself, and then come here to check your answer, solution, explanation, da. All right, let's get started. So first problem, what is the product of the above reaction, right? So if you really think about this reaction, we actually have a aldehyde, right? So first things first, usually whenever we are actually talking about or thinking about reactions, the best way to actually think about them is to first identify the functional groups, right? So once you have identified the functional groups, then the second step is to think about what type of reactions happen when those two functional groups are actually bonding or reacting with each other, right? So we've got an aldehyde and an alcohol. So let's think about what product we actually would form if we actually had an aldehyde and an alcohol. So then in the product formation, right, we would actually form a hemiacetal, because we know that if you have 1 mole of an alcohol and an aldehyde, then we actually form a hemiacetal, right? And if we actually had 2 moles of alcohol, then we would have formed then we would have actually formed, hold on, I want to put my iPad on D&D. Then we have actually formed the acetal. But right now, we are actually forming the hemiacetal. And if we were to identify which of these product is actually a hemiacetal, so that's an option D, and that is the correct answer for this problem. Right, okay. So if you think about these two, again, we have a ketone this time, and we have an alcohol. So again, there are two options, right? Again, with ketone and alcohol as well, it can form hemiacetal or acetal based on how many moles of alcohol is actually used in the reaction. So if there's 1 mole of alcohol, right, then we form hemiacetal. Otherwise, you'd form full acetal. So let's see what the options are. Do we have an option of forming a full acetal and a hemiacetal? So if you look at option A, right, CH3C, OCH3CH3, okay, so OCH2H5. So we see that, okay, they're forming a OC2H5 over here. So they're forming the ether bond of the hemiacetal with C2H5, which is correct. But the new alcohol is the one which actually forms the acetal bond, right? So if there's OC2H5, and then there's already a presence of C2H5, so we should already have like C2H5. So the problem here is that you cannot really have two, you really need to have two ethyl groups in the product, and it's not present in option A, so that's definitely not the correct answer. Option B, for sure not, right? The ethyl group kind of just disappeared over here, so that's not the answer. The third option, right, now if you really think about it, it is, okay, and this is a ketone, of course, not an answer, right? So it also helps if you're going through process of elimination. For option C now, if you really think about it, right? We have OC2H5, the new acetal coming in, or the new group coming in, the ethyl group coming from that alcohol, which is representative of OC2H5 of alcohol here. And then we have C2H5, which is already here, right? Which actually is this group right here. And then the double bond O, if it is a hemiacetal, converts to an OH. And that's exactly what happens here. So hemiacetal then is the correct answer, meaning they were reacting with one equivalent of alcohol. Okay, the next option. Reaction of a ketone and amine, right? So when this reaction happens, the reaction of a ketone and an amine in the presence of an ether, so what actually happens in the product is that ketone and an amine, right? So we always form imine when these two functional groups are actually going to react. So now this is an imine, right? This is not an imine. This is also not an imine, and this is an amide. So the only correct option here is option A, and we can even think about how we are actually forming that product. So that actually is C double bond N, right? So think about just removing a molecule of water, H2O, remove that, subtract, remove that water, and then connect the two bonds, connect the structure. So we've got that C double bond N, right? And then there's this ethyl group, CH2CH3 over there. So that is the product of that reaction. For problem 4, all of the following properties are responsible for reactivity of carbonyl bond in propanone. So, okay, 1, 2, 3, this is propanone, except the fact that carbonyl carbon is electrophilic, which is true. It's a true statement. So we're looking for a false statement, right? So the carbonyl carbon is electrophilic. It is true. The carbonyl oxygen is electron withdrawing, which is also true because oxygen is electron withdrawing. The resonance structure of the compound places a positive charge on the carbonyl carbon. Yes, if we were to draw out a resonance, it would actually look like this, right? So it does place a positive charge on your carbonyl carbon. I'm not sure like why I had like a question mark in the problem, but the dash electrons are mobile and are pulled towards the carbonyl carbon. So the electrons are actually never pulled towards the carbonyl carbon. The electrons are actually pulled more towards the carbonyl oxygen, right? So option D is the correct answer because that's the false statement that we're looking for in all of these options. All right. Next problem. The above reaction is an example of, okay, so clearly this is not esterification. It is actually tautomerization. Elimination, it's not elimination, or dehydration. Dehydration is just removal of water. So this actually is an example of true tautomerization. And you should know what esterification is by definition. Formation of an ester is esterification, right? Elimination is when you actually carry out the elimination reaction or removal of a group like HBr, water, something like that. That would be an elimination reaction. Dehydration, again, removal of something like a water species, that is dehydration. So answer B is the correct answer for this problem. For the next option, which of the following reactions produces the above compound? Okay, if you really think about it, this looks more like an aldol condensation, right? So every time you form an alpha beta hydroxyketone, right? Add the ketone, if you have alpha beta hydroxyketone, then sorry, beta hydroxyketone, right? Not alpha beta, but like beta hydroxyketone, that reaction or that product is usually formed via a, what is it called? A aldol reaction, aldol condensation, aldol condensation reaction. So if we think about which of these reagents basically will give us the product that's over here. So if we think about it, we have one, two, on this aldehyde, we have two carbons with the C double bond O and the hydrogen. So we have an aldehyde of two carbons, and then we have one, two, three, four. Four carbons, which is also an aldehyde. Okay, so this is more like a mixed aldol, right? So one, two, three, four. Okay, so if you think about it, this CHO can be representative of this C double bond O and the H, right? The aldehyde piece. And then if you really think about the alpha hydroxy, right, forming a negative charge in the first step of the aldol reaction, then attacking the carbonyl of that compound. Will that give us the product? So let's think about it. One, two, three, one. Hold on. One, two, three. Okay, one, two, three, and four. The fourth carbon actually is a C double bond O and the hydrogen. And if I were to add the base, right, obviously you would need a base to carry out the aldol condensation reaction. So the base would go over here, then go over there. Okay, so that's the first step. And then in the second step, we have the second reagent, which is CH3C double bond O and the hydrogen. So then when the negative charge actually attacks at the carbonyl carbon, right, which also is like delta positive, delta negative over here, then you would actually form the product, which is CH3C, and then double bond O, hydrogen. Okay, and then there's a carbon over here, which is the new bond that we're now forming. Okay, and then there is a OH here because this carbonyl will convert to a hydroxy group, and then this is the CH3. So is that the product that they want us to form up top? Not really, right? Yeah, so option A is not going to give us that answer. I think, okay, so if we really think about it, we want an aldehyde piece. Okay, if I actually break it down over here, so I want one of the aldehyde to have three carbons over here, right? These three carbons will convert to the hydroxy. So we need an aldehyde. So if I really think about it, I need an aldehyde to have those three carbons. And then for the other one, I also need another aldehyde, right? That will also have three carbons, or one, two, three in total. One, two, three, because one, two, three. One of the hydrogen over here we can create like a negative charge over here that will, if that attacks over here, so that should be able to produce this product because that's how the aldol condensation works, right? So then if you think about the option D, right, which actually has one, two, three carbons and then one, two, three carbons. So both the aldehydes with one, two, three carbons and one, two, three carbons, they will actually produce that product. So option D is actually the correct answer for this problem. And because this is like a single correct answer type problem, so that's why I'm just not looking at the other options. But of course, even if we did look at other options, right, we can definitely verify that really fast. For option C, will that also give us the product or not? One, two, three, the third carbon has one, two, three, the third carbon has the carbonyl and CH3. The second carbon has an aldehyde, CH3C double bond O, and the hydrogen. Okay. So if we were to create a negative charge, which species should act like a nucleophile, which species should act like an electrophile for us to actually form that product? So one, two, three, and the OH carbon negative. Okay, so it does make more sense if this species can actually act more like the negative charge over here, if this was the nucleophile, would attack at this carbonyl carbon. But of course, that's not giving us the product because we are just forming. Oh, that's definitely not giving us a product, right? So if we did the opposite, there was a negative charge over here in the aldyl condensation, and we attacked over there. Would that give us the product? So let's think about it. So we have C double bond O, H, and we have a CH2, and then we have a C, okay, and we have an OH, a CH3, and then 1 and 2. Is that the product that we want? Again, that's not the product that we want, so that's not the correct answer. So I'm not going to go over 2. Again, you have to look at both the possibilities of using one of the aldehyde or one of the ketone as a nucleophile and the other one as electrophile, and then do the opposite to kind of make sure that that is not your product of the reaction. All right, next problem. What is the product of the above reaction? This is a very simple reaction, right? I'm not even going to explain it. It is an oxidizing reagent. So really fast, aldehydes, when using very, very strong oxidizing reagent, will undergo full oxidation. And then we have a hydrogen over here. So that will very quickly convert to a 1, 2, 3, a carboxylic acid, right? So 1, 2, 3, 1, 2, 3. So we have 3 carbons and carboxylic acid. So then, okay, two carbons of the ethyl group, right? And the C double bond O, H, and the carboxyl group. Heating an aldehyde with zinc in HCl. So this is also a very classic Clemmensen reduction reaction based out of memory. So the answer is an alkane. That produces an alkane. That's the correct answer. Which hydrogen atom in the above compound is the most acidic? Okay, if you really think about this, we do know that the alpha carbons of carbonyl compounds are the most acidic, and that's why we always form a nucleophile, right? If a base is added, the base reacts with always the most acidic proton because there are always these different possibilities of protons that can be abstracted, and it's this one too, right? So the negative, and if it was to abstract the HA, it would generate like a negative charge here. That negative is not stable at the carbonyl carbon, but this negative is actually stable at HB, or at that carbon, at the alpha carbon of carbonyl. So HB is actually the most acidic proton for this compound. So what is the product obtained in the above reaction? So this is a reduction reaction using lithium aluminum hydride. For the reduction to happen, a lithium aluminum hydride will actually just, add the H here and H here. So we'll convert your ketone to an alcohol. So that is the final product. So option B is actually the correct answer, where we just converted that to an alcohol. This is not an alcohol. This is dihydroxy products, which are also not the correct answer. And they just like fragmented the molecule, which is also not what lithium aluminum hydride does. So option B is the correct answer here. Next problem, what is the reaction between benzaldehyde and excess of ethanol? So we do have benzaldehyde, so we have CH double bond O, and excess of ethanol, meaning C2H5OH. So that in the presence of anhydrous hydrochloric acid, what is the product of the reaction? In the presence of anhydrous HCl, there is no water involved, right? And again, if you really think about it, this is what an aldehyde. Okay, wow, 3 problems on acetal formation. Actually, it's like one of the really important reactions of carbonyl chapter, right? The reaction of an aldehyde with an alcohol, and it says excess, which means that 2 moles can react, right? Or the maximum capacity of alcohols can actually react in this reaction, and the maximum capacity for that is 2 moles. And so we know an acetal is formed if 2 moles of, or 2 equivalents of alcohols are used. So if you think about the acetal formation, then option B is actually the correct answer for this problem, because that is an acetal, right? This is hemiacetal, so not the correct answer. Also hemiacetal. Also with the incorrect options actually, and I that's my bad. This is not the correct answer because the acetal would actually have only one benzene, right? But over here we actually have two, so that is incorrect. So the acetal that would actually be formed would have two equivalents or two bonds with the OC2H5. So the two bonds with the ethoxy groups, right? So right, one ethoxy over here, the second ethoxy over here. So then we have the benzene here. So okay, that actually is the correct answer. That this is also an acetal, and this acetal is the correct answer. Okay, again, you don't want to rush through the problem and like skim through it so you see like the functionality that's correct and just choose that. Obviously, you want your atoms to make more sense as well. So option D is actually the correct answer. A student investigates the reactivity of carboxylic acid derivatives, okay, with an aldehyde and an aldehyde, okay, by reacting hydrazine with the benzaldehyde and a student investigates the reactivity of carboxylic acid derivatives and aldehydes by reacting the hydrazine with benzaldehyde and okay, benzoyl chloride. So hydrazine is reacting with benzaldehyde, which is over here, and benzoyl chloride, so which is benzoyl chloride. Okay, and which of the following statement is true about this reaction? Both compounds undergo substitution reactions but arrive at different products. So it is true, right? When we react with the hydrazine, they will arrive at different products. Both compounds undergo elimination reaction but arrive at the same product, which is actually not true. Unlike benzaldehyde, benzoyl chloride undergoes an elimination reaction because chlorine is a good leaving group. Chlorine is a good leaving group. So when the nitrogen, yeah, is going to react, the nitrogen of hydrazine will actually react, right? So this will go here. The carbonyl oxygen will go up over here, the electrons, and then because we know Cl is a really good leaving group, so then this will come back, kick out the Cl. So what we actually have is a Cl as a really good leaving group. So there is a substitution reaction happening, a replacing of a amine of the hydrazine with the Cl, right? So option D is actually the correct answer. So we're not really seeing the elimination, but we're actually seeing substitution reaction. But are these two products actually giving us the same answer? So if we have a benzaldehyde, then they both compound undergo substitution reactions. Oh, okay. So the first one, right, the benzaldehyde itself is not undergoing a substitution reaction because this is only undergoing an addition reaction. But then for the benzoyl chloride, it will undergo substitution first, and then if there are more moles of hydrazine, then it will undergo the addition reaction. Okay, all right. So then option D is actually the most appropriate correct answer for that problem. Okay, so then assuming a meticulously anhydrous environment, which of the following could be used to form 3 ethyl hept 6 3 ol? Okay, let's think about that. Okay, is that's probably okay. Which of the following could be used to form 3 ethyl? Okay, so like nomenclature is really important, right? Like they can add a nomenclature problem in any chapter. The first things first, when you're preparing for MCAT, you have to make sure you know nomenclature for Orgo, for you to get Orgo right, okay? So never like miss out or like skip over nomenclature just because it's easy, you think you're gonna do it later. You need to do it the first thing because then you need to practice every problem, including nomenclature, with the nomenclature, because the more you practice, the better you get at it. And the better you are, the less afraid you are, and it's going to be easier for you to tackle the problem head on. Do not leave it for later. This is like And also, do not leave things that you find are hard for later. Do the hard things first. Eat your frog first thing in the morning, right? And then do other things. So that's like the most important thing right now. When you're preparing for MCAT. Okay, so which of the following could be used to form 3-ethyl hept 6-ene 3-ol? Okay, so we have 7 carbons. 1, 2, 3, 4, 5, 6, and 7. Hept 6-ene. So on your 6th carbon position, we have a double bond, 6-ene, and 3-ol, meaning at the third carbon, there's an OH group. At the third carbon, there's also an ethyl group, right? 1 and 2. Okay, so if you think about what options are going to give us the correct answer, so let's really think about it. Option A, if I actually use the Grignard reagent, right? So this is a reaction of a Grignard with a ketone. So then I basically have a negative charge here and there is a positive charge here. And for carbonyl, the distribution of negative and positive, we know it's always delta positive, delta negative. The negative charge attacks the delta positive carbon over here, right? So we are forming a product which will actually look like this. So then we've got a OH here and 1, 2, and 1, 2. Okay, is that the product that we want? Yes, right? If you really think about it, 1, 2, 3, 4, 5, 6. Am I missing a carbon? 1, 2, 3, 4. 1, 2, 3, 4 carbon. Okay, and then that carbon adds to the carbonyl. Yeah, I am missing a carbon, right? So this is actually the correct answer. And if you really think about it, so I've got 1, 2, 3. So the third carbon has OH, the hydroxy group, and the ethyl group. 1, 2, 3, 4, 5, 6, 7. And then the 6 and the 7 actually has like that double bond, which is also what we want in the final product. So option A. And if I see one more possibility of the correct answer, that only tells us that all of the above is more likely the correct answer for this problem. So I'm going to do that really fast. Again, I have a carbonyl and I have a Grignard, right? So there is a negative charge over here. Attack on the carbonyl, so that will actually give us a hydroxy on that carbonyl. So if I draw out the product, I'm going to create this hydroxy group, and then we've got an ethyl group, and then there is a CH2 and a CH3, right? And that's exactly what I want in my final product. So there's a 100% probability that option D is actually the correct answer, because using 2 of the options, we got the compound that we actually want to form as the final product. And I'm gonna let you solve this yourself. Actually, never mind. I'm just gonna do it right now really fast. With the ester, right, the reaction of aldehydes, or sorry, Grignard, is slightly different. So we react that twice, right? First, we undergo a substitution reaction. The reaction undergoes a substitution reaction. So we would actually form this as the product. Okay, and then so we have got C double bond O and then CH2, CH3. Okay, so that's the first step. That's when this reagent, which we have 2 equivalents of, which also says 2 in front of it, when it reacts first, this is what would be formed, right? And then when it reacts the second time with the Grignard, we effectively have that the synthesis of, or the regeneration of the starting material, not really, actually, hold on, regeneration of this starting material with, again, this as a second reagent for this reaction. So then the reaction of this and this, of course, will give us the same final product, which actually is this final product, right? So you would actually just generate that final product in the reaction, right? So again, that also is the correct answer for that problem. So we've got option D as the correct answer. And so with that, that is the last problem for this chapter. I'm also starting a 7-week MCAT preparation tutoring, and we'll be going through every chapter. We'll be going through notes for every chapter. We'll be creating Anki decks, And we'll also be going over a ton of practice problems from Kaplan and a few other textbooks. So if you're interested, if that's something that you're interested in, you want me to help you guide it through every chapter of Orgo 1 and Orgo 2. So it's going to be fast paced. We'll meet twice a week, and then there'll be unlimited support for you guys. So if that's something that you're interested in, hit me up and send me an email. I'll be very shortly running my ads on Instagram, but I don't know if I'll be doing that through YouTube. But if that's something that you are interested in, reach out, and I will see you guys in the next video, which where we will go over carboxylic acids. And I promise to make that video sooner than this one. And so until then, take care and keep growing, keep learning. Bye now.